Problem is called minimum size subarray sum. We are given an array of positive integer nums and a positive integer target. We have to return the minimal length of a subarray whose sum is greater than or equal to target. If there's no such subarray, we have to return 0 instead. So basically, subarray is defined as continuous sequence of numbers in the original array. So, for example, in the example 1, we have target 7, and we have the nums. We have the following nums, and as we can see, the smallest subarray, continuous sequence, basically 4 and 3, have the minimal length, and their sum is in this case equal to 7. For example, we also have 2, 3, 1, and 2, which have the sum equal to 8, which just by still fulfills the requirement that the sum has to be greater than or equal to the target, because the target is 4. But we have a subarray of length 4, which is larger than 2. So this is an optimal. 4 and 3 are optimal subarray. So the same goes for the example 2. We are looking for a target 4, and basically we can have a subarray only containing one element, because in the initial array we have the element 4, which matches the target. Now in the example 3, we basically have 8, 1. So the maximum sum that we can make from the array is 8, because all the numbers are all the elements in the array are 1. So we can never reach actually a sum that's larger or equal to the target. So by the problem statement, we just return 0. Now the constraints are the following: the target is from 1 to 10 to the 9th, and the length of the array given by the input is from 1 to 10 to the 5th. So we are kind of looking for linear time complexity here. The elements in the array are from 1 to 10 to the 4. Now, when it comes to the finding a subarray with a certain property in an array, or basically a substring with a certain property in a string, we are approaching the problem by using the sliding window approach. And in the sliding window approach, we basically have two pointers. Let's just mark them as I and J, which correspond to the start and the end of the window. The window can be a fixed size. It can be it can vary in size. It really depends on the problem that you are trying to solve. So to basically define the sliding window for the problem, there are a few things that we have to check. First thing is that the property that we want to calculate. In this case, the property of the window that we want to calculate is the actual sum of the window. So we will basically have a variable that will track the sum of the window. The second thing is that are we trying to find the minimum or maximum window? So in this case, we are trying to find the minimum window. So when we have a minimum window problem, we are basically trying to expand J until we get the property that fulfills the condition. So in this case, we are moving the J as far as we have to until we have a subarray starting from I and ending in J that has a sum smaller or equal, or greater or equal than the target, because that's the property that we want to fulfill. If we have that, then we have fulfilled the first requirement. The second thing of the sliding window algorithm when it comes to the minimum windows problems is that we then try to minimize the window. And to minimize the window, we are moving the I boundary, so the start boundary, to the right, therefore shrinking the window. And as we move the I boundary to the right, we are also checking if we still fulfill the condition. If we still, for example, in this case, if the sum is greater or equal to the target. If it is, we keep on shrinking the window and we are updating some global variable, let's just say min length. And at the end, after basically J reaches the end of the array, we will just return this min length as the final result. So we'll see how this algorithm performs on one of the examples. So we'll take the first example from the problem statement, and we will declare our I and J to point at the first number. So therefore, pointing at the first number in the array. We will also declare our window sum, and we will initialize it to be 0. Also, the minimum length global variable that will track basically the length, the most favorable length that we have. We will initialize it basically to the length of the array, which in this case is 6 plus 1, because basically that's the any length will do. Even if we have to take the whole array, it will be smaller than this minimum length. So for the initial value, this is a good default. So then basically we are iterating, and we are moving through the array, and we are moving the j, and we are basically updating the window sum by the elements, by the value of the elements that we are iterating over. So basically the first thing that we will do, we will change the j to point to 1. So we are moving it to the right. But before we do that, we will add whatever the previous value of j was pointing to. So in this case, it was pointing to 2. So we will update our window sum to be equal to 2. Next, we see that like 2 is still smaller than the target. Let's just say that the target that you are looking is the same as in the first example from problem 16, so it's 7, and the window sum is still smaller than 7. So we have to move j to the right more. So basically, we are then turning j, instead of having it set it to 1, we are setting it to 2, and we are adding the previous value. So in this case, it was 3. j was pointing to 3, so the window sum will be now 5. But that's still smaller than the target. So we will keep on moving our j. So now it will point to the third element, but for that we will just add 1. So the window sum will now be 6. Still smaller than the target. But the next time when we add the value that j is pointing to, so in this case is 2, we will have window sum 8, which is larger than the target, and we move our j to the right side. So now it's 4, and we are trying now, because we have a minimum windows problem. We will try to shrinking the window by moving the starting I pointer to the right, as long as the condition that window sum is larger or equal to the target. But before we do that, we will update the minimum length. So in this case, the minimum length can be calculated by just doing j minus 1. So in this case, we have 4 minus 0, because basically j is pointing now to this. So it's basically outside our window, and this is the window that we are looking. And if we just do j minus 1, we will get the total number of elements, which in this case is 4. So we will update the minimum length to be 4, because 4 is smaller than 7. And after that's done, we will move I to the next position. So I is not pointing to the first element, now it's pointing to the second element. So we set its value to 1. But because now we don't have the contribution of the first element in the window sum, it stops being a part of our window. We have to decrement the window sum. So instead of having 8, we will have 8 minus 2, basically the value of our first element. So our window sum will be 6, and 6 is now smaller than the target. So basically, we invalidated the window, and we stop shrinking the window. Now we'll basically continue the same process that we had before, hitting a window sum that's larger than the target. We will just add to the window sum the element that the j is pointing at right now. So it's pointing to 4. So our window sum will now become 10, and j will be pointing to the last element. Okay, so 10 is now larger than 7, so we are starting to move our I. Now I is pointing to the first element, so we are now, basically this is our window now. And we have to exclude the contribution of the first element and move the I to the next element. Before we do that, we will try to update the minimum length. But we see here that 4 minus 1 is 3, and 3 is 5 minus 1 is 4, because now j is pointing to 5. Basically, it's outside of our window, and that's the same length that we have already stored. So we are not updating the minimum length here. So basically, then we are trying to shrink, and we are deleting the contribution of the element that I is pointing right now. So it's pointing to this element. So we are doing 10 minus 3, which is 7. So in this case, now I will be pointing to the third element. The next time when we still have 7 is basically equal to 7 to the target, so we have still valid window, and we can try to update the minimum length by using the j-1 formula. So in this case, we'll have 5 minus 2, which is 3. So we have only 3 elements, 1, 2, and 4, which have a sum equal to 7, which corresponds to the target. So we update our minimum length to be equal to 3 now. And the next time when we move our I, we will basically decrement 7 by 1. So we will get the window sum to be 6, which is smaller than the target. And we will move I to the next element. So in this case, I will be pointing to the element here. So let's just make another array to make it clearer where our pointers are at. So in this case, I is pointing now to this element here, and j is pointing to the last element. So the next time when we add the contribution of the element that j is pointing to, we will basically have the window sum 6 plus the last element, which in our case is 9. So we will basically 3, and the 6 plus 3 is 9. So it's still larger than the target, and we will move j to the end of the basically outside of the array. So basically we know that this is the last chance that we have to have a smaller window. So because now we are checking this window here, and the total value is total sum is 9. So we are trying to make it smaller by decrementing the total sum by the element that the I is pointing to. So in this case, we will have 9 minus 2, which is equal to 7. So it matches the target, and we will move I to point to the second to last element. So in this case, we will have 6 minus, because j is pointing now to 6, it's the basically outside of the array, and I is pointing to the fifth element with the index 4. So we'll have the minimum length of 2, and we can update the minimum length to be 2. Basically, those are the last two numbers that we have in the array. It's 4 and 3, because I is now pointing to the second to last element, and j is pointing to the element with the index 6, which is basically outside of the boundary of the array. So in this case, basically we just updated the minimum length, and we are stopping the algorithm, because the next time when we decrement next time when we try to shrink the window, we will have 7 minus 4, because I is pointing to the 4. So 7 minus 4 will be 3, and that's smaller than 7. So we have to break out of the, we already invalidated the window, so we have to break outside of the loop. Now, basically, because we are only traversing the initial array once, we will have linear time complexity, and we are not storing any additional data structure, so we'll have constant space complexity. We will declare our minimum length to be basically the length of the array plus 1, and we will declare our pointers to point at the first element of the array, and also the window sum will be initially set to 0. Next, we will traverse as long as j is in boundary of the input array, and each time we will basically add the current element j is pointing to, and after that we will increment j by 1, basically just move it to the next element in the array. Then we will check if we have a valid window, and as long as we have a valid window, which in our case is a window that has the window sum larger or equal to the target, we will try to first update the minimum length by using just j-1 formula and the current minimum length that we have stored in the variable. Then we will try to shrink it, and because we are shrinking it, we are moving the I pointer to the right. But before we move, we have to remove the contribution of the current element that the I is pointing, basically the start of our window, because it's in the next iteration it will be no longer part of our window. So we basically just decrement the contribution of that number, decrement it from the window sum that we have, and we continue that as long as we have a valid window. Then after we are done with the first loop, basically j is now outside of the input array, we will just check, we'll just return a minimum length modulo the length of array plus 1. We are doing this because we can have a case like in the example 3 where we cannot really form a subarray, or basically using the whole every single number in the array. We can still form the subarray that adds up to the target or larger sum than the target. So in that case, the minimum length will stay as it is, and we will just return a 0. In any other case, we'll just return the minimum length that we have stored in our variable.